Hello, I am Dr. Abhishek Sharma. In this video, we will discuss the very important subsection of DPCM, transmitter and receiver. This section is considered as predictor. So let us start. This predictor is also considered as transversal Now, we all have studied Taylor series. Now, what is the significance of Taylor series? So, this theorem states that if we have infinite sample of past values of a signal, let us suppose a function, then we can exactly predict the future value. Now let us suppose that MT is an analog band limited continuous signal. Band limited continuous signal. Okay. And after sampling, this signal with a rate of this, after sampling this signal with a rate of 1/ts samples per second. This is nothing but sampling frequency or Nyquist rate, because this is the minimum required sampling rate according to the sampling theorem. Now, as this is the sampling rate, if we want to find out the value of mt plus ts, let us suppose if we want to find out a value at m of t plus ts, then with the help of Taylor's theorem we can write it as m of t plus ts upon factorial 1 m derivative of mt plus ts square upon factorial 2 m double dot t, which is the second derivative of mt, and so on up to infinity. Now as ts is a very small time, that means we can ignore ts square, ts cube, and so on. So the above equation will become m of t plus ts, or we can approximate it as m of t plus ts into its derivative. Now it is clear from the above equation that m of t plus ts can be obtained with the help of its past values such as mt and its derivative m dot t. Now as we have already know that let us suppose this is my continuous time analog band limited signal MT, and if we take the sample, then it will look like let us suppose these are the sample values. Then let us suppose this is M of 0, and this sample will be M of TS, and this sample will be M of 2TS. Because this interval is 0, let us suppose this is t equal to 0, and this is TS, this is 2TS, this is 3TS, this is minus of TS, this is minus of 2TS, and so on. Okay, now we can also represent the above section in this manner. Let us suppose this x-axis is nothing but the kth number of sample. That means if this, let us suppose that M0 is represented by kth sample, the next sample will be M of, this sample will be M of k plus 1, and again another sample will be M of k plus 2, and so on. Similarly, here the sample will be considered as M of k minus 1. That means we can represent M of kts in terms of mk. M of k plus 1 ts in terms of M of k plus 1. Now with the help of this equation, we can again write it as M of t plus ts is equal to M of t plus ts m dot t. Now we know that derivative of a signal can also be represented as limit t f of t. Let us suppose this is not f, this is m of t minus m of t minus ts divided by ts. In this way we can also write it as, if we take the number of sample of mt, then it may also be represented as m of k in terms of number of sample minus m of k minus 1 divided by ts. So let us suppose that this is the value of this one, m dot t, and we can put this value in this equation. So the above equation will become, let us suppose this is your m of k plus 1, and as t is the common term in all after sampling, then we can represent the number of samples, the sample values in terms of numbers. That means mk plus 1 can also be presented as m of k plus ts into m of k minus m of k minus 1 divided by ts. Now these two terms will be cancelled out. So now mk plus 1 term will be considered as m of k plus m of k, or we can write it as twice of mk minus m of k minus 1. From the above equation, it is clear that the prediction of k plus 1 sample is possible with the knowledge of kth and k minus 1th sample. Now in general, if we have infinite number of sample values, then we can predict the future exactly. In general, m of k, let us suppose the future, then it can be represented as a1 m of k minus 1 plus a2 m of k minus 2 plus a3 m of k minus 3 and so on. That means if we have infinite previous values, sample values, then we can predict the future. This right hand side can be equated as, or you can say that the right hand side can also be known as, can also be considered as the predictive value of mk, that means mk. Now, as we have seen that if exact value of the sample is mk, then its predictive value can be obtained with the knowledge of the past sample values, which can be the output of the predictor. That means we can also extend the above equation as mk is equal to, approximated as a1 m of k minus 1 plus a2 m of k minus 2 plus a3 m of k minus 3 plus up to the nth. Let us suppose there are n sample, then an m of k minus n. Now the above equation is an nth order predictive filter. This is nothing but an nth order, the characteristic, you can say the input output relation of an nth order predictive, or you can say predictor, nth order predictor. If we want to draw the block diagram of this nth order predictor, then let us suppose this is your input. This is your input, then here the sample mk is present, and we can take the delay by ts, and we can get m of k minus 1. As m of k minus 1 is multiplied by a1, this term is a1. You can also vary the amplitude of a1, or you can change the value of a1. So in this case, this a1 can be considered as tap weights, tap weight. Delay by ts again, you will get m of k minus 2. Suppose this is a2, this is another tap weight. Let's suppose that this is the nth delay, which is delay by ts again. Now if we add these values, we will get m k. This is the block diagram of the predictor, and m cap k is the estimated or predictive value of mk with the knowledge of past samples. The above block diagram is considered as transversal filter or transversal tapped delay line. Filter. This is a very important and very important topic. You can say the important, why I am saying that this is 2 times. This is very important because there is a very huge application of this tap delay line filter in future. Now after this, as we have defined what is tap delay line and what is the prediction and what is a predictor, now let us discuss that how can the signal to noise ratio of PCM is linked with signal to noise ratio of DPCM. Now in continuation we will discuss the SQNR relation of DPCM with PCM. Now, in case, let us discuss the scenario that how much SNR, how much SNR is improved in DPCM. In comparison of PCM. So for this discussion, we have to calculate the step size for pulse code modulation, which was considered as delta PCM earlier, and it is equated as twice of MP divided by L, where MP is the peak value, positive peak of a single tone signal. That means in PCM, for a single tone signal having peak value minus MP to plus MP, the delta PCM is defined as twice of MP by L. Now, in DPCM, we are quantizing the difference between two consecutive samples. That means the step size for DPCM is defined for the difference between consecutive samples. That means twice of dp upon L, where dp is nothing but the difference between two consecutive samples. Now, if you divide del of PCM divided by del of DPCM, then it will be equated as M of P upon dP. From the above expression, this expression, it is clear that del of DPCM is dP upon MP del of PCM. This means that for the same quantization levels, step size del of DPCM is given by dP upon MP of del PCM. As dP is smaller in comparison of MP, that means del of DPCM is less in comparison of del PCM. Now the quantization noise for DPCM if it is given by del square DPCM divide by 12, then it will be dp square by mp square 12 del of PCM square. That means dp square upon mp square will be multiplied by quantization error of PCM, quantization noise of PCM. Clearly, quantization noise for PCM. That means in this case, the quantization noise for DPCM, quantization noise for DPCM will be reduced by a factor of dp upon mp whole square. Thank you.